Good?
Yeah.
Yep, pretty good. Happy Wednesday. Middle of the week, ready to roll. Yeah, so we'll probably pretty much finish up chapter 6 today and do a little work on this on Friday, a little in-class worksheet, and then jump right into acids and bases and pH. And then we're at our first exam, and then we move on to organic chemistry, so it's pretty cool. Pretty fun stuff ahead of us. So right now we're working on understanding nomenclature of molecules and ionic compounds. Today we're going to lay the foundation as to why this is important that we're studying all this chemistry stuff. We're going to see this amazing concept called electronegativity. Electronegativity, again, is the driving force on how we can predict electron movement. So I'm not a big fan of memorization, but we do have to memorize electronegativity values, but I'll show you how. It's not super hard, it's not boring, it's actually pretty straightforward, and why that's important. Because the entire organic chemistry section and biochemistry section is really the movement of electrons. So today we're going to see why it is and how it is that certain atoms like electrons more than others and what we do with that. So it's very important in a chemical setting. Okay? So let's jump in and let's talk about the concept of electronegativity. What is it and why do we really care about this? So electronegativity big word, electronegativity. How much does an atom actually want electrons? So electronegativity is an atom's desire for electrons within a bond. Okay? That's memorization. Electronegativity is an atom's desire for electrons within a chemical bond, within a bond. Say that again. How bad does an electron, or how bad does an atom want electrons in the context of a bond? That's what we're looking at. Now, if you took 1200 or another form of GChem, you might have heard the term electron affinity. Electronegativity and electron affinity are slightly different. Electron affinity is just how much an atom wants electrons, not within the context of a chemical bond. Electronegativity is specifically between two atoms, which of those atoms wants those electrons more. Okay? So when we look at something like methane, and we draw a good Lewis dot structure for methane, we see methane in its tetrahedral arrangement looks like this. We saw ammonia with this lone pair in the plane, and it looks like this. And finally, we saw water with its lone pairs in the plane, and its hydrogens coming out and going back. Okay? So those three molecules are the lens through which we're really going to understand carbon, nitrogen, and oxygen. As I've been building on this concept of our window into really biological systems, really goes through those three atoms. Okay? Specifically carbon, and then what's hung on carbon in the form of nitrogen, oxygen, phosphorus, and sulfur. Okay? So with that, I'll just tell you right away, carbon, nitrogen, and oxygen do not share electrons equally. I was basically kind of bringing a story into this with this whole idea, this whole concept of the protagonist and the antagonist. The protagonist of our story for this class really is carbon. Carbon really is the hero. Carbon is the atom that shares the best. It's in the most unfortunate location on the periodic table, but it overcomes that by sharing. But here's the thing. Carbon really doesn't hold its electrons very well. It really wants to give them away and share them. It really is a giving little atom. Nitrogen and oxygen are much more aggressive. In fact, oxygen is the second most narcissistic element on the periodic table. Okay? It is a bad friend. It's like that friend that always takes and takes and takes and never gives. We always know that. We know that type of friend. Oxygen steals. Nitrogen steals. Carbon gives. So through that, we have this concept of electronegativity. You see, these electrons, remember, all this line is a pair of electrons. That's what that means. Okay? The question is, where do those electrons prefer to be? Closer to hydrogen or closer to carbon? That's what electronegativity is helping us with. Now focus on this, because you might be asking, why do I care about that? You care about that, or you should care about that, or I'll challenge you to care about that, because as I have element X and element M. Don't look up there, they're not up there. Those are two letters that do not represent any element. Notice this. If my electrons are perfectly between those two, they're sharing perfectly equal, then neither of them has the electrons more than the other. Okay? We're going to call that a nonpolar covalent bond. I'll write that down, but I want you to hear that. Notice that word, non-polar. When you think of polarity, what comes to mind?
Magnets.
Magnets. You saw me bring the magnets in, didn't you?
Water.
Water is very polar, right? Dimethyl sulfoxide, and then dimethylamide. There's so many molecules that we have out there, but one of the biggest one is water. Watch what happens. If I'm sharing equally, those electrons are not going any direction. But watch what happens. As those electrons begin, let's say M wants the electrons more than X, notice now what's happening. The electrons are going towards the M, causing this to have a partial negative charge. Why? This isn't calculus. We're not getting into partial derivatives. We're not going to integrate this, which would be fun. But why? Why does the M all of a sudden start to have a little bit of a negative charge?
If there's more electrons on that side, then the charge is slightly more negative.
You got it. What charges the electrons? Aren't electrons a negative? So if that M is starting to have those electrons more, it's becoming more negative. In its wake, what is happening to X?
It's becoming more positive.
It's becoming more, who said that? Okay, couldn't see it with the mask. It's becoming more positive. So this is starting to form a partial positive. Notice, as the electrons move more and more towards, let's do it this way. Yeah, that's okay. As they begin to move more and more, notice what's going to happen. My charge is going to get larger, right? So here's one of the myths we have to break from all chemistry up to this point. There is no such thing as a purely ionic compound. Typically in chemistry, we have this line that I drew, and I drew it very clearly in nomenclature. Ionic compounds are made from metals and nonmetals. Covalent compounds are made from nonmetal nonmetals. We have different nomenclature. That's how we know the difference between an ionic compound and a covalent compound. But the problem with that is we think there is this class of compounds called ionic and this class of compounds called covalent. That is a myth. It really is a continuum of the difference in electronegativity between the two atoms. We happen to arbitrarily put some lines and some sticks and some markers along the way, but the whole process is where are those electrons? And we're going to go from 0 when it's equal to 0.1 to 0.2 to 0.3 to 0.4, 0.5, 1, 1, 2, 3, 4, 5, 6, 1.1, 0.2, blah, 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 all the way up to the most ionic compound we can have is the one that has the highest electronegativity with the one that has the lowest electronegativity. Okay? Even that one's still about 92%. only 92% ionic. It's still not purely ionic. Okay, so now let's do our little exercise so we can actually use this and begin to look at methane, ammonia, and water and see if we can begin to understand why they have the physical properties they have. Because here's one of the things you need to ask yourself the question. On these two molecules, they look very similar. All right, they look very similar. In fact, if you calculate their molecular weights, but again, this isn't a class in stoichiometry, you know that carbon is 12.01, 1111, so that is about 16 grams per mole, okay, or 16 atomic mass units per molecule. Nitrogen is 14, 15, 16, 17, you're about 16 and 17. You're not that much heavier. 1 atomic mass unit. Oxygen is 16, 17, 18, so it's around 18 grams per mole. So 18 grams per mole, 17 grams per mole, 16 grams per mole. But here's the cool thing. This one has a melting point, or boiling point, I'll use melting point of 0 degrees centigrade. This one has a melting point of negative 78 degrees centigrade. This one has a melting point of negative 296 degrees centigrade. What in the world explains that? It makes no sense. You can't tell me that 1 atomic mass unit between these changes their internal attraction for each other that much. Something else is going on. Ah, that's called electronegativity. Because these bonds are not equal. So here, let's go to the periodic table and let's all memorize it. This won't take very long. If you listen to me, this isn't very hard. If you tune me out, this will be difficult. It's not difficult. Okay, so when I was in high school, the highest you could get was a 4.0. Okay? I just got my son's grades. He's at the Ambrose School. I don't know if you guys know what that school is. It's a classical Christian school. He had a 4.61 at the end of it. I was like, how do you do that? Then look at my daughter's, and it's 4.27. I'm like, when I was a kid, it was like 4.0 is the highest you could get. Which is kind of cool. But nonetheless, 4.0 in my world was the class standard, okay? I guess nowadays, because of concurrent credit, AP, and all that, it's different. I didn't have those when I was a kid. And I got kicked out of 2 schools. So when you look at this, fluorine is your class standard, okay? So what do you think fluorine is going to have for electronegativity? Since I brought up the GPA thing, 4.0. Fluorine is 4.0. It has the highest electronegativity of any element, any atom on the periodic table. It is 4.0. It is the class standard. Easy to remember because that's the class standard, 4.0. Okay? So here we go. We're going to go across the top row all the way to lithium. It goes down each element across that row by an increment of a half. Again, that's not difficult because I can subtract 0.5 from 4, and that gives me 3.5. And I can subtract 0.5 from 3.5, and that gives me 3.0. And I can subtract 0.5 from 3.0, and that gives me 2.5. And I can subtract 0.5. See what I'm doing here? It's not very difficult. Class standard of 4.0, 3.5, 3.0, 2.5, 2.0, 1.5, 1.0. That is easy. That shouldn't be difficult for anyone in this room. Start with 4.0, I go down by half across that row. Okay? We all good with that? Next row is a little more difficult. We're going to memorize it too, and then we're going to stop. Because again, this class, for the most part, we don't really dip below this line. All right? We, for the most part, are going to live right up in here. This is where we live in biological chemistry. So we'll go down to the next row. When you go down from fluorine, chlorine goes down by a whole 1. So it actually is the same as nitrogen, so it's 3.0. So you go from 4.0, an A, to a B. So chlorine is the B student in the class. This is 3.0. So again, 0.5, 1.0, all right? Now, here's where it gets a little, not tricky, but you just have to pay attention. It's going to go like this. It's going to go 0.5, 0.4, 0.3, 0.3, 0.3, 0.3. See what I just did? 0.5, 0.4, 0.3, 0.3, 0.3, 0.3. So 0.5, so I'm 3.0, down 0.5, so what's sulfur? 2.5, down 0.4, 2.1, down 3, 1.8, down 3, down 3, down 3. Boom. You just memorize the first two rows of the periodic table. Not difficult, but so incredibly important and foundational, again, to our understanding of what's going on over here and really what's going on in biological systems. Now, those are all experimentally derived. We know those from experiments called the Pauling scale. We'll get into how we derive that, how he derived that. There's a couple different scales, but that's the one we primarily use. You have this arbitrarily, remember, hydrogen. It sits up here on its own, and it's 2.1. You just have to memorize that. Excuse me. You could almost say that if I have 3.0, 2.5, 2.1, you could say, oh, it's the same as phosphorus, if you want. That helps. But it is 2.1. Okay? Let's do it one more time. Right? Because it's easy for you to watch me do it, but we have to, again, engage in it. So I'm going to start with the class standard at 4.0. Then I'm going to go down 0.5. So 3.5, 3.0, 2.5, 2.0, 1.5, 1.0. Okay? I'm going to drop down from fluorine to chlorine at 3.0. So full jump down to the B in the class. 3.0. Then I'm going to go down by 0.5, so I'm 2.5. I'm going to go down by 0.4, so I'm 2.1. Go down by 0.3, so I'm 1.8, 1.5, 1.2, 0.9. Arbitrarily, remember, 2.1, and just memorize the first two rows of the periodic table. Neon, or helium, neon, and argon do not have electronegativity. They're happy. Remember, their energy levels are full. They don't have a desire for electrons. Okay? They don't make bonds. We don't make bonds on those until we get to krypton and xenon. Have been a couple argon, but they don't last very long. They die pretty quickly. So krypton and xenon are big enough that they can have their electrons stolen by fluorine, by the way. Xenon difluoride is a cool compound. I've worked with it several times. Okay? Are we good? So now let's go back and see what's going on over here. If electronegativity is an atom's desire for electrons within a chemical bond, now I can begin to see what's going on with these bonds. Okay? So when I take my knowledge of electronegativity and I apply it to these molecules, notice what happens. Carbon is 2.5. Hydrogen is 2.1. Okay? So in that context, if you look at the hydrogen-carbon bond, or in this case, if you look at where the electrons are just slightly closer to carbon than they are to hydrogen. Okay? So they're just slightly closer to carbon than hydrogen, not in the middle. Right? So that sort of sets up a little tiny positive and a little tiny negative. In fact, it's so small, we consider it nonpolar. All right? So, on our continuum of a difference, delta, difference in electronegativity, our first stick in the sand is a delta En of 0.4. Okay? Anything that has 0.4 or less, including 0.4, is considered nonpolar covalent. Okay? So this is nonpolar covalent. That's our first line, our first definition. Again, it's a continuum. We just happen to put a line at 0.4. Okay? Well, hey, that's interesting. Notice 2.5 minus 2.1 is what? 0.4. So this is 0.4 delta En. Therefore, anything with a carbon-hydrogen bond is going to be nonpolar covalent. Oh, well, that's kind of cool. And when we get into organic chemistry, that'll even make more sense, because if you look at a molecule like propane, some of you might know what propane is. Propane is 3, pro is 3. We'll get into organic chemistry, we'll learn how to name all this, see how cool this really is, and why we're building on this. But if you look at propane, there's propane, 3 carbons with a bunch of hydrogens. Notice, all of these bonds are 0.4, okay? That causes propane to be a non-polar molecule, which is why something like grease and water don't mix. That's why when you have your oil and vinegar salad dressing, you have to shake it up before you put it on the salad, because they don't mix. If you want to get them to mix, you have to agitate them at a very high level. We call those emulsions, and that's exactly what shampoo is. Shampoo is an emulsion between a grease and a non-grease. Okay, that's why it likes the grease of the hair, and it likes the water of the shower, and it removes the grease. And by the way, since we're in a flu season, washing your hands with soap and water does not remove bacteria or viruses. Let's just be clear on that. I get kind of upset that people think if you just wash your hands, you're going to be good. Soap removes grease. That is it. It's the temperature of the water, it's the agitation of the soap in the hot water, it's the time that your water is being agitated on your hands that helps it, or an additive to the soap, like ethyl alcohol, like isopropyl alcohol. It's something else that's been added to the soap that helps kill the bacteria, not soap. I have to have this talk with my kids a lot, because they think that they run their hands under cold water in a bar of soap, their hands are clean. All you did was just move the germs around, and you still have quite a bit of grease on your hands, because I looked at my iPhone screen, and it has a bunch of thumb smudges on it. All right? You have the greasiest hands I know. Why don't you guys learn how to wash your hands? Anyway, so that's just one of my little things. We will talk about emulsions and soap when we get into the lipid chapter, which is super fun, because it's really practical in that area. That's just one of my little pet peeves. Back at the ranch. This is a non-polar molecule, which is where we're headed with this, okay? It's a non-polar molecule because all of these bonds are non-polar. Even look at the difference with this bond here. What is carbon's electronegativity? 2.5. What is carbon's electronegativity? Yeah, so the delta E in between this is 0. That's a completely covalent bond. No polar at all, right? So our first stick in the sand is at 0.4. 0.4 and less in a difference in electronegativity is considered nonpolar covalent. We tracking? Our next stop along the way is nitrogen. Well, let's just hop over to nitrogen. Nitrogen is 0.5 more than carbon, so what is nitrogen's electronegativity? 3.0. Okay, 3.0. So nitrogen is 3.0. Hydrogen is still 2.1. Notice, and if you want, you can we make these little vectors, and they're little tiny vectors. They have an arrow and they have a positive, and it simulates, wrong way. It simulates the direction those little electrons are headed, okay? And again, 0.4 is not, we just consider that nonpolar. It is moving a tiny bit. I mean, it's just slightly towards the carbon. Not enough to make this any kind of polarity. Once I get to nitrogen, watch what happens. What's my delta En here? 0.9. Yeah, 0.9. So here, I have hydrogen, nitrogen. Notice 0.9, I'm starting to move more towards nitrogen. Okay? How much more? Well, by 0.9 on my electronegativity scale. So we need to have a new category. If I'm 0.4 or less, I am nonpolar covalent. Any questions so far? Am I talking too much? I know I talk a lot, but this is really important to me. This is a real foundational day. Real foundational day. Okay, so our next place is right about here. Okay? This is a magical place. This is 1.8. Okay? So if you are less than 1.8 to 0.5, and by the way, just so that you know, the 1.8 is one, this is not an ish, this is 0.4. The 1.8 is an ish, okay? So I won't give you one right on 1.8. I've seen textbooks teach it down to 1.7. I've even seen them teach it almost a 2. Okay, so that one can move a little bit. Our book uses 1.8, that's what I'm going with. Okay? This category here now is what we call polar covalent. Polar covalent. Meaning this bond right here is heading in this direction. Okay? When it heads in that direction, it causes a partial positive and a partial negative. It makes a polar bond. Okay? Polar covalent. Meaning the electrons are moving towards the nitrogen, causing this to be partially negative and this partially positive. Tracking? And so going back to the whole magnet thing, the movement of electrons is heart of chemistry. So if I could predict where those electrons are or how they're going to behave or where they're going to go, I'm golden. That's chemistry. That's all it is. That's all acids and bases are. Bases are electrons, acids are no electrons. Electrons like to go. Bases attack acid. Boom. There's 95% of chemistry right there. All right? So if I know where my electrons are, I know what my chemistry is doing. So here we have it. We have electrons. We have the absence of electrons. We've all played with magnets. So if I now have a polar bond, I know that the positive and the negative can be attacked by another negative. There you go. I just made a new bond between this and that. Okay, that's chemistry. That's all we're doing, right? These are getting weaker. Oh, they actually do still hold. But you can see that that's all that chemistry is. Chemistry is playing with magnets. Isn't that weird? That's all we're doing. We have to be able to predict how strong those magnets are. And right now we only really have one magnet, that nitrogen-hydrogen bond. But nonetheless, that's what it is. Okay? So this polarity here tells me that I know that actually no, these electrons are going to go do some mischievous things. Okay? Next stop is water. So what's the electronegativity for oxygen? 3.5. What's the electronegativity of hydrogen? Hasn't changed, 2.1. Whoa, ho, 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 ho. Look at that thing. What do you think? Huh, that's interesting. It is a delta En of 1.4. Wow. So here we have the electrons really approaching that oxygen. So that causes my vector to be larger. Okay? And so that causes my charges to be larger. See how that works? If my electrons are moving more towards the oxygen, they're becoming more negative. The oxygen is becoming more negative, leaving a bigger positive. So my vector gets bigger because my electronegativity is getting larger. Make sense? So you're seeing a continuum of bonding, and that's exactly what bonding is. Bonding isn't ionic or covalent. We have to know where the electrons are to know what category we're in. Okay? If I'm above 1.8, my final category is what you would call, and what you probably learned, as ionic. Okay? And this is where we get into ionic, or the naming of ions, the naming of cations and anions. We spend a lot of time on the polyatomic anions, the cations, how we put those together. So watch how this happens. So I'll just continue the trajectory after 1.4 is my delta En. Okay, it's my change in electronegativity. So notice I've gone from non-polar covalent to polar, slightly polar covalent to very polar covalent, but I'm still not ionic. So if we jump down and watch what happens here. So when we did our memorizational work, what was sodium? Anybody remember what sodium was? We can do it again. 0.9. Yeah, 0.9, good. So look at sodium chloride. Watch what happens with sodium chloride. Sodium chloride. Sodium chloride. Where are the electrons in sodium chloride? Huh, I never thought of it that way. Cool. Well, because we've memorized the first two rows of electronegativity values, I know that chlorine is my B student, and I know that sodium, so what's my delta En for sodium chloride? What is it? That's kind of cool. 2.1 is my delta En. So what is sodium chloride? Is it nonpolar, polar covalent, or ionic? Hey, that makes sense. Sodium chloride is an ionic compound. Why? Because the difference in electronegativity puts it in the category of ionic compound. Okay? So you put sodium chloride in water, it dissolves. Sodium falls apart, chlorine falls apart, and water surrounds it. Surrounds the anion with the hydrogens and the cation with the electrons and the oxygen. Any questions on this? Because this is really foundational. Okay? Now, we still probably don't know why it is that it takes so much energy to break up this thing. Okay? But maybe it's starting to click. If I have really, 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 really weak magnets, and these pens are magnets, they're just really weak, how much attraction do I have between them?
Hardly any.
Like none, right? Or hardly any, right? There's just, you can't even feel it. There's a London dispersion, there's an attraction there, but nothing that you can actually sense with my senses. Okay, so it doesn't take much energy to break that apart, right? Meaning it doesn't take a lot of heat or energy to break a nonpolar bond apart. I don't have to add energy to the system to get the molecules to come apart. That's what boiling point or melting point is. How much energy do I have to put into the lattice in order to get a phase change from solid, liquid, gas? All right? But now notice what happened when I jumped to ammonia. All of a sudden, it takes quite a bit more energy to break up ammonia. Well, why? What happened to my magnet strength? Did it increase or did it decrease? It increased. See, what's happening here is this negative and this positive find another negative and positive, and they like each other. And there's an attraction there. So just like there's an attraction here, it's going to take more energy to break this up. And so now, all of a sudden, I actually have to pull on it to break. That takes energy to break that apart. So it takes more energy to break this apart because there's a polarity here and there's an attraction of the opposite. Okay? By the time I get here, notice that's getting to be a really strong magnet. And it takes a lot of energy to break up water. In fact, water does something we'll see here in a few minutes called hydrogen bonding, which is one of the miracles of chemistry. All right? So it really takes energy to break that apart. Meaning I have to put energy into the system in order to go from solid liquid to gas. Does that make sense? So the stronger the magnet, the more energy I have to put in to break the molecule's attraction apart. All right? And the bigger my difference in electronegativity, the more energy it requires to break that apart. We good? Tracking? Okay. Let's make it harder. So let's complicate it. You build a foundation and, right? A little more, we're building. We're building. We're building the foundation of chemistry in these 3 chapters. All right. How many of you have played tug of war? Pretty much everybody. Okay, me too. All right. What happens when you play tug of war with 2 people? And I don't know how you play tug of war. When I play tug of war, and this is old school, we put a red handkerchief on the rope, and you had to get the red handkerchief to move. That's the way I played it as a kid. I don't know if you do that anymore. You just try to pull each other in the mud or whatever. So if you have 2 people pulling on a rope at the same strength, where does the handkerchief go? Where? It doesn't go anywhere, right? It doesn't matter how strong this guy is and this girl are. If they are equally pulling, the handkerchief goes nowhere. Does that make sense? Okay, so watch this. If I make a molecule and a good Lewis dot structure for carbon dioxide, which we already saw, There's carbon dioxide. The farthest away I can get two electron domains from a central core is on a linear trajectory or linear plane, right? But now let's use our electronegativity and see something very interesting about what happens here. If I know that carbon is 2.5, that would be a 5. Funny how sometimes your hand does it, but I don't know why it does that sometimes. And oxygen is 3.5, and oxygen is 3.5. Notice my delta En for these is what? 1.0. That puts me here. It puts me in the polar covalent realm. But stay with me. That makes this a polar bond. It's a polar covalent bond. But here's the thing. If you have two equally poling atoms pulling the exact same, the handkerchief, the red flag doesn't move. So you can have a polar covalent bond, but have a non-polar molecule. Let that sink in. It doesn't matter how strong the two people are on the ends of the rope if they're pulling the same. They could be really weak if they're the same, it's not moving. If they're really strong and they're the same, it's not moving because they neutralize the opposite vector. Because really what's happening here, if you go back to your physics, your left-hand rule or whatever it is, this is a vector. The electrons are moving that direction, but they're moving this direction at this exact same amount. Therefore, the flag in the middle does not move, so it makes it a nonpolar molecule because the electrons have to move in order for this to be a polar molecule. Does that make sense? Sort of? Okay. All right. Probably no one in this room, I've never had someone in this room do a three-way tug-of-war. It's possible. Three-way tug-of-wars are a little bit more difficult, but they're there. What happens with a three-way tug-of-war? Well, three-way tug-of-war is when you have a rope and you tie a knot there and put the flag on the middle where the other rope is coming in. And what happens if you have three equal parties pulling on that knot or that red flag equally in all directions? What happens to it? Again, it does not move. It doesn't matter how strong it is or weak it is. If it's equal, it neutralizes it. So an example of that, a classic example of that, would be something like boron trifluoride. If I make a good Lewis dot structure for boron trifluoride looks like this. That is the Lewis dot structure. Again, boron does not have to obey the octet rule. It likes 6, not 8. So that's why it has 6 around it, not 8. Perfectly happy molecule. But what's the electronegativity of boron? What is it? 2. 2.0. What's the electronegativity of fluorine? 4. Holy moly. That is a massive vector going that way. In fact, that is such a strong vector that puts that bond into the realm of what? 4 minus 2 is what? It's ionic. It's a very polar bond. But what about boron trifluoride as a molecule? Nonpolar molecule. Doesn't matter how strong the bond is, if it's pulling equally, it neutralizes the charge. Okay?
Oh, okay, so it's a matter of class. I think I get what you're trying to say. It's not, when you say, I'm having a really hard time trying to articulate this,
Cool.
but I think I get what you're putting down.
Okay, good. I like it. When it clicks, it clicks. Now, Watch what happens the minute I take one of the vectors and I change it. What about boron difluorohydride? What about this molecule? What just happened to that molecule? Boron is 2.0, hydrogen is 2.1. So small, you can't even see it. So what happens? Does the flag move?
Yes.
Absolutely. That's a bomber polar molecule. Okay? So here's one of the things of chemistry that's really hard to unteach. Chemistry is not letters and bonds. Chemistry really is playing with lava lamps. I'm so thankful that lava lamps made a comeback. They were really popular when I was a kid when they first came out. And we used to sit for hours and watch those things bloop and blop and cool and heat and bloop. That is chemistry. Chemistry is magnetic blobs attacking other magnetic blobs. It's just really hard to articulate a blob. So we draw HCl like this because we're happy with our little Lewis dot structures and we think we're doing so well with that. But really what it looks like is a little blob there and a big blob there. That's what hydrochloric acid looks like. It's got a massively negative region here and a massively positive region here. That's what it looks like. And because it has this massively big giant blob over here and this massively little positive blob over here, this chlorine says, I'm going to go somewhere, I'm going to leave you in my wake. And so hydrogen comes off and it says, I'm a proton now, I'm an acid. And that's really what's going on here. Okay? So when we look at something like this, it's better to see it as this. In fact, red is typically negative in these electrostatic potential diagrams. So you see really what's going on here is this massively big blob of red going to this little tiny blob of blue. That's what it looks like. But we don't like that. It's hard to quantify and draw blobs and mean anything about it. But really, that is what chemistry is. It's one blobby magnet attacking another blobby magnet. We quantify the blobbiness by electronegativity. Does that make more sense?
Yeah.
So a covalent bond, like this bond here, or this bond here on the carbon-carbon, if we made it in blobbiness, would really look like this. It would be this equal distribution of those electrons. As electronegativity increases, this kind of starts to pinch off until you're starting to separate that out. All right? But again, it's a continuum. It's not one or the other. It's not a binary system. It's a continuum. Okay? And so that's why the whole idea of electronegativity becomes so important. All right? So, when we start to see these vectors start to have relation with other vectors of opposite attraction. Okay, so when we talk about this, we have a couple different ways of quantifying this. So let's take something like formaldehyde. Formaldehyde shows a really nice example of this. So formaldehyde So if you draw something like formaldehyde, formaldehyde is COH2. So formaldehyde is CCOH2. That's formaldehyde. So now when I look at formaldehyde, I can use my electronegativity, I can use my Vesper geometry, and I can begin to look at this molecule in a whole new way. I know that this oxygen is 3.5, I know this carbon is 2.5, and I know this hydrogen is 2.1. That tells me that these bonds are non-polar covalent, and it tells me this bond here is polar covalent. So since that bond is polar covalent, that sets up a delta positive, because again, the electrons are moving in that direction with the vector. That sets up a delta negative up here. So when I put formaldehyde in with more formaldehyde, formaldehyde says, cool, I'll go ahead and orient in the jar of formaldehyde. I'm going to orient myself this way because there's now an attraction between this positive carbon, the negative oxygen, this negative oxygen, and the positive carbon. There's an attraction there because they're little magnets. It takes energy to break up magnets. Formaldehyde is a polar molecule, therefore formaldehyde says to water, come on in, let's have a party. Put your hydrogen there, but go ahead and put your oxygen up there, and we'll party like this. Okay, so formaldehyde and water really like each other. In fact, it's really hard to get all the water off of formaldehyde. The one that a lot of people might know is this molecule is called ethyl alcohol. That's the common ingredient in the solvent we call booze. This molecule is very polar. It's very polar because I have a distribution here of 2.5, 3.5, therefore delta 1.0, meaning that vector is heading in that direction. This is 2.1, this is 2.1, 3.5, so therefore this one's a massive vector going in that direction at 1.4. So what happens is ethyl alcohol, and this is all nonpolar. So ethyl alcohol says, wow, I'll go ahead and bring hydrogen in here, oxygen in here, so it loves water. So ethyl alcohol and water are so mixable, likable, that you can only distill it to about 95%. And back in the day, they used to call that Everclear Jungle Juice, 181. Okay, that was an alcohol you could actually buy. I don't think you can buy it at the Idaho liquor store anymore. We used to get it because we'd use it as solvents in the organic lab. But you can only distill to about 95. And by the way, we have 200 proof alcohol in the lab. We have it under lock and key. But we do it in a special way. We fake out the water. We actually add benzene to it. And then we distill it off the benzene, and the water sticks to the benzene, and we get the ethyl alcohol off. We kind of fake it out. It's called an azeotrope distillation. It's kind of cool. All right? And it's anhydrous. You actually put it on your hand, and it turns your hand white because your tissue absorbs all the water, or the ethyl alcohol absorbs the water out of your skin. Super, super hygroscopic. It's kind of cool stuff. So what happens here then is this all sets up a molecular attraction. Now, that said, there is one of the most special molecular attractions that we're going to see all through organic and biochemistry, and it is called hydrogen bonding. And I'm going to end with this, so hang on for this ride. It is the coolest thing. Hydrogen bond. We have 5 minutes to land the plane, and we're going to make it. Okay, so there are 3 entities that hydrogen bond, and that's it. Okay? So, notice my delta En here is 0.4. My delta En here is, I'm going to put it on the other side. I'm going to put it on the left side. 0.4. Put it right there, just keep it out of the way. Okay? My nitrogen hydrogen is going to be 0.9. All right? My oxygen hydrogen, 3.5 minus 2.1 is 1.4. Okay? Fluorine hydrogen is going to be 1.9 because it's 4.0 minus 2.1, 1.9. So, these hydrogens here are super special. Not that one. Carbon-hydrogen bonds do not hydrogen bond. Oxygen-hydrogen, hydrogen bonds. Oxygen-hydrogen, hydrogen bonds. That's what this little dash is right here. This little dash is a hydrogen bond. This is a dipole attraction. Dipole attraction. Okay, there's no hydrogen bonding going on there. Dipole. This is hydrogen bonding. Only 3 entities hydrogen bond. It is the NH, OH, the FH. Because in organic chemistry, and life chemistry, hydrofluoric acid will kill you. We don't typically play with HF gas, okay? So really, we only have to remember two, the OH and the NH. When we see an OH bond, we think, oh, that's important. When we see an NH bond, oh, that's important. So let me show you where this applies. There is a molecule in our bodies that comes from the degradation of heme, and it looks something like this. And when we get back into the cooler organic chemistry part of this class, I'm going to bring some of these molecules back so you can begin to see them and how cool they really are. So this molecule right here is one of the molecules that is actually very important for us to see in a biological setting, because this molecule is called bilirubin 9-alpha, okay? That's bilirubin 9-alpha. Has anybody in this room heard of bilirubin?
Yes.
Where have you heard of bilirubin?
Liver and jaundice.
Where?
The liver.
Delivery, yep, in labor delivery and jaundice, right? 1 out of 4 of us in this room had a high level of this compound in our blood, and the danger is it crosses the blood-brain barrier and it causes brain damage, okay? What we do today is we have these things called Billy suits or Billy light. It's a blue frequency of light that you put the infant in for a while until the enzyme that's sluggish kicks in that actually puts a big sugar up here so it makes it soluble. Here's why that is so powerful. This bond absolutely is massively important. So when you draw bilirubin like this, you might be thinking, well, I still don't see what you're doing. Well, good, let's do it a different way. Okay, so if we take this compound, and draw it like this, stay with me. I know this is where it gets really cool. This is where chemistry kind of starts to actually mean something more than just a bunch of nomenclature and electronegativity memorization. Okay, you see what I just did? This carbon right here is like 2 thumbs of a paddle. And so this bilirubin actually goes like this, goes, and it folds in on itself. And when it does that, notice what it does. It takes those hydrogens and watch. Oh, it's so cool. Just the exos. Okay, check this out. Okay, what entity did I say was really important for hydrogen bonding? There's 2 of them. Oxygen, hydrogen, and nitrogen, hydrogen. So here's what happens with this molecule. This molecule says I have an oxygen, hydrogen here. I'm looking for electrons. So it comes in and it makes a strong bond with that oxygen. Nitrogen, hydrogen, the other special one, says I'm looking for electrons. Oh, oxygen, you've got them. I'm going to come in and form this massively strong bond with those. This one over here says, cool, same thing, same thing, same thing. I didn't draw that one, okay? So with bilirubin, what happens with bilirubin is the molecule doesn't sit here and flop around. It actually locks around and it folds in on itself, and it cloaks all of the polarity inside all this grease. And so the molecule cloaks itself as a greasy molecule, and it crosses over the blood-brain barrier, causing brain damage. And it was a nurse who noticed that the infants that were sitting closer to the windows in the neonatal ward were going home faster. And so in that ward, they started to move all of the kids closer to the windows. And you know what they found out in the 60s as what was happening? The light was taking the Einwagen bond here and causing it to flip to a Einwagen bond, and it went like this. It went, and it broke up the matrix of hydrogen bonding, causing the polarity to go out, and the water likes it, and it was able to get rid of it. Isn't that incredible? All from an observation of a nurse because of this fact of hydrogen bonding.
In your wife's work, because I used to work in the NICU and PICU with
Yeah.
Billy babies, is it still the typical 3 days under the UV lights before?
You know, I don't know the actual regiment,
Okay.
but I know when they put them in the heater, the little things, yes, they're.
Typically it was like 3 days.
3 days.
I think the temperature, because the temperatures would drop drastically.
We'll drop down. That's cool. That's cool application. Okay, we'll pick this back up on Friday. Make sure you're up through chapter 6 because chapter 6 we'll review it on Friday. Okay? Good.